lecture 5, 110N. We are going to talk about source transformation, which I had already introduced last time. We are going to talk about superposition theorem and nonlinear one ports, and then work out a few examples. The topic of source transformation we have already introduced. This is the application of Thevenin's theorem to a voltage source and Norton's theorem to a current source. No, it's the other way around. Application of Norton's theorem to a voltage source. We have said that if there is a voltage source V in series with a resistance R, then this by Norton's theorem is equivalent to a current source V by R in parallel with R. This is the transformation of a voltage source to a current source. On the other hand, if I have a current source I in parallel with a resistance R, then this is equivalent to a voltage source whose value is IR in series with a resistance R. These two constitute what is known as source transformation, and in many occasions, source transformations are sufficient to solve a network. You don't have to write either the branch formulation or the loop formulation or node analysis. You don't have to do any of them. Simple source transformation and common sense, of course, are enough to solve the network. And let's take an example to show this, how source transformation enables you to solve a network. And this is one network which we have taken repeatedly as an example. It's the same network that we shall take. 24 volt source, 6 ohm resistance, 15 ohm. Then we have a 1 ampere current source in parallel with a 10 ohm resistance, and it is this current that we wish to find out. We have solved this network earlier, perhaps in the tutorial class also, to find out the current I by various methods, branch currents, loop method, nodal method, and so on and so forth. Now by source transformation you will see that we don't have to write any equation. If we apply Norton's theorem to the left of this line, Norton's theorem, that is the voltage source in series with a resistance, then in shunt with another resistance, then you can easily see that the short circuit current, if I short circuit these two terminals, the short circuit current would be 24 divided by 6, which is equal to 4 amperes, and then the equivalent resistance, the Thevenin resistance or the Norton resistance, shall be the resistance looking back with the 24 volt short circuited, which means a parallel combination of 15 and 6 ohms. That means 15 times 6, that is 90 divided by 21, which is 30 by 7. So 30 by 7 ohms, and then you have the 1 ampere current source and the 10 ohm resistance. This is the current that I wish to find out. Now you notice that both these current sources are in parallel, 4 amperes and 1 ampere. So the equivalent current source, we can convert these two into a single current source of value 5 amperes, 4 plus 1, and then the circuit, then the equivalent circuit becomes 5 ampere in parallel with a 30 by 7 ohm resistance in parallel with a 10 ohm resistance, and this is I, and therefore I can be obtained by inspection, that is 5 multiplied by 30 by 7 divided by 30 by 7 plus 10, which is simply 150 divided by 70 plus 30, 100. So this is 1.5 ampere. We have got this result again and again. But this illustrates how source transformation is able to reduce a network to a form where you do not have to write KCL, KVL or any loop formulation or node formulation or branch formulation. So, source transformation, which in effect is the result of Thevenin's and Norton's theorems, are extremely useful in network analysis. One consequence of linear resistive network or linear networks is the application of the so-called superposition theorem. More than stating it formally, it is important to understand it. It states that if you consider a linear network, in a linear network, the current or voltage in any branch, the current or voltage in any branch, any resistance, is the superposition of the corresponding quantities, that is currents and voltages, due to individual sources, each acting independently with other sources replaced by their internal resistances. Try to understand this, you will write later. The theorem concerns a network in which there are more than one sources, all right. Maybe there are a few voltage sources, a few current sources and so on, and you want to find out the current or voltage in any branch of the network. Then the superposition theorem says what you do is take one source at a time, and kill all other sources. What does killing mean? Replacing a voltage source by a short circuit and a current source by an open circuit. Independent sources only are to be killed, dependent sources are not to be touched. Once again, exactly like Thevenin's theorem and Norton's theorem, all right. So, it says if you have a number of dependent sources, then determine the response or the current or voltage that you wish to determine due to each source independently, all right, killing all other sources. Then you add all the responses, that is, you superpose all responses. The total response shall be the algebraic sum of this, all right. This is what in a sense is superposition network, superposition theorem. And the most important thing to be remembered about the application of this theorem is that it must be linear. The superposition in fact is a consequence of linearity, all right. As you will see later, linearity implies two principles. One is superposition and the other is homogeneity. Linearity involves superposition and the other is homogeneity, which says superposition means that the response of a given network, by response I mean the voltage or current in a given branch, this branch may be considered as the load. The voltage or current is the superposition of all voltages and currents caused by each source independently of all other sources, all right. And homogeneity implies that if the cause, that is if the source or excitation as it is called is multiplied by a factor alpha, then the response should also be multiplied by a factor alpha. For example, if a 12 volt source gives rise to, let us say, 1 milliampere at a certain point in the network, then a 24 volts should give rise to 2 milliamperes, all right. This is called homogeneity, and linearity implies both. So, a zero source or zero excitation should lead to zero response, all right, which means that linearity, not only the relationship is linear, but the straight line must pass through the origin. For example, y equal to mx plus c, although it is an equation to a straight line, it does not represent a linear network because it does not pass through the origin. When x is 0, y is not equal to 0. The presence of this constant c makes a difference. All right. An initially charged capacitor again is not a linear system, as you shall see later. But let's not go further into this. Let's concentrate on superposition. Superposition also allows you to solve for a network or analyze a network without writing elaborate equations or without solving simultaneous equations. As you shall see, superposition along with source transformation sometimes can solve very complicated networks without writing a single loop equation or node equation and so on. So these are tricks of the trade, and we shall illustrate superposition by means of the same example that we have been taking again and again. 24 volt, 6 ohm, 15 ohms, 1 ampere, and then 10 ohms. We want to find out the current I. Now superposition says, just by looking at the network, you see that there are two sources. One is a voltage source and the other is a current source. So we wish to find the current I. I therefore should consist of two parts. I should be equal to I1 plus I2, where I1 is the response to, let's say, 24 volt after killing the 1 ampere source. In other words, removing the 1 ampere source or open circuiting the 1 ampere source. That is I1, and I2 correspondingly is the current in the 10 ohm resistor when the 1 ampere source is killed. 24 volt source is killed, which means that short circuiting. So let's find out these two currents. One is 24, 6, 15, the 1 ampere source is killed, so it's opened, and then you have a 10 ohm, and this current is I1. Obviously I1 is equal to 24 divided by 6 plus, what is the parallel of 15 and 10? 150, that is also 6, alright, multiplied by this current divides into two resistors, 10 and 15, so 15 divided by 25, which obviously I1 is equal to 1.2 amperes. Pretty smart. 5 to 30 divided by 25, maybe you are right, 1.2, okay, agreed. Alright, then the other part is that we kill the 24 volt source, so we short circuit this, and then we have the 15 ohm, then we have the 1 ampere source and the 10 ohm resistance, and this current is I2. So what is I2? Well, obviously the 1 ampere source divides into two branches. One flows through 10 ohms and the other through the equivalent of 15 and 6. How much is that? 30 by 7. So what we have is, this is equivalent to this circuit, 1 ampere in parallel with 30 by 7 in parallel with 10 ohms, and this is I2. Therefore my I2 shall be equal to 1 multiplied by 30 by 7 divided by 30 by 7 plus 10, which is equal to 30 by 100, right? If I multiply by 7, 30 by 100, which is equal to 0.3 ampere. And therefore by superposition says if you have found them independently, simply add them up. Alright, simply add them up. In other words, the required current I shall be equal to I1 plus I2 equal to 1.2 plus 0.3 equals to 1.5 ampere, the result which we are getting again and again. Here also you see we didn't have to write any loop equation, node equation, branch formulation or anything. We didn't even make any source transformation. We simply applied superposition. All right. So superposition does help you to solve problems. There are some other examples in the tutorial sheet, number 2, particularly on the back, and I urge you to try solving some of them by superposition. Next we consider, we have talked about linear network. Let's see what happens if we have a non-linear network. And to keep life simple, we first consider a nonlinear one port. A nonlinear one port, which means a network having available only 2 terminals, only one port or a pair of terminals, a nonlinear network NLN. Okay. Obviously, if this is a resistive network, if this network is a resistive network, then you can call it a nonlinear resistor. All right. Let's consider first a nonlinear resistor. There is no special symbol for a nonlinear resistor, so we will simply say Rn, all right, to indicate that it is a nonlinear resistor. Now, a nonlinear resistor obviously does not obey Ohm's law. Ohm's law says V should be proportional to I, all right, and the proportionality constant should be Rn. Here in a nonlinear network, this is not necessarily so. V and I are not necessarily related linearly. In fact, one could have a situation like this, which is obviously not linear. All right. Such a characteristic is that of an incandescent lamp. If you take an ordinary bulb, a 60-watt bulb, and gradually increase the voltage, measure the current, all right, you will get a characteristic like this. An incandescent lamp is a simple example of a nonlinear resistor where V equal to Ri is not valid. Another common example is that of a diode. A diode whose symbol is this. A diode, if you connect a voltage source V and measure the current I, if you connect a voltage source V and measure the current I and vary V, then the current shall also vary, and one will see that one gets a characteristic like this. It's very small. This is IV characteristic. This is V, I beg your pardon. This is I and this is V. IV characteristic is such that when V is negative, very little current flows. When V is positive, current increases almost exponentially. All right. This is obviously a nonlinear resistance. There are many other examples of nonlinear resistance. There are examples of nonlinear inductors and capacitors also. For example, if I make an inductor, how do I make an inductor? I take a core like this and wind turns of wire around this. If this core is non-magnetic, for example a piece of pencil or a piece of wood, then the flux current relationship phi versus I is fairly linear. Okay. On the other hand, if this core consists of iron, which is a magnetic material, then as you know, iron, the amount of flux with increasing current tends to get saturated. That is, That is, what happens is that up to a certain extent, while it's linear, and then the flux tends to get saturated. Similarly in the other direction, it tends to get saturated. And you know that if you bring back the coil, if you bring back the current to the previous value, it does not follow the same path, and that's this famous hysteresis phenomenon. All right. The point that I am mentioning is that the flux versus current relationship, which should be linear for a linear inductor, if you use iron as a core, then it tends to become non-linear, and therefore an iron cored coil is an example of a non-linear inductor. Similarly, as you shall see later, you can make a semiconductor device in which the capacitance is proportional, well, in a linear capacitor, the charge should be proportional to voltage. C should be a constant, it should be independent of voltage. You will see semiconductor devices later in which the capacitance is a function of V. If the capacitance is a function of V, then obviously Q versus V plot shall no longer be a straight line, and therefore it becomes a non-linear capacitor. So we can have a nonlinear resistance, we can have a nonlinear inductor and a nonlinear capacitor. Let's concentrate our attention on first nonlinear resistors. Nonlinear resistor. How does one characterize a nonlinear resistor? Well, one of the ways is to use, instead of analytical method, is to use graphical method. For example, suppose we have a diode. Suppose we have a diode in which the VI characteristic is like this. This is VI. For negative V, the current is very small. For positive V, the current increases almost exponentially. And then what you do is you apply, let's say, a sinusoidal voltage to the diode. That is, you have a diode, this is the symbol for a diode, you apply a sinusoidal voltage, V. Sinusoidal voltage means that the voltage varies like this, let's say, 2. Suppose the voltage varies like this. This is sinusoidal. Ignore this slight deviation from sinusoidalness. This amplitude is equal to this amplitude. Now, if you plot the corresponding current, obviously at this peak the current would be this much. Alright, so if you extend this horizontal line, and at this peak the current is this much, very small, and therefore the current waveform shall no longer be sinusoidal, it would be distorted, it would be like this. There would be very little of current when the voltage is negative. The current flows merrily when the voltage swing is positive. In other words, the diode, this nonlinear resistor, favors a positive voltage. It discriminates against a negative voltage, and therefore this diode, the diode, acts as what is known as a rectifier. That is, it accepts the positive half of the voltage, it rejects the negative half of the voltage, and that's why you could convert an AC to a DC, a unidirectional current. And if you put a DC meter, then you shall measure the average value, okay. So a diode, a nonlinear resistor therefore can be used as a rectifier. Similarly, you can have other examples of nonlinear resistors, and a nonlinear resistor, the network analysis problem can be solved graphically. We shall see other examples. We shall take a fairly complicated example a little later of a nonlinear of a circuit containing nonlinear resistors. But let's look at an analytical method. This is a graphical method. Is this graphical method understood? You look at the voltage variation. This is the voltage axis. So you look at the voltage variation, the corresponding current, you plot it, and you see this is what you wanted to find out, the current I. So if the characteristic is given graphically, then you can find out the output. Here the input is a voltage and the output is a current. One can also do this as you will see later in electronic circuits, that if I have a characteristic which is not linear, but let us say a characteristic like this, alright. Obviously this is not linear, but what one can do is one can approximate this by a number of straight lines. For example, this part is fairly straight, so what you do is you approximate this by a straight line like this, and this part can also be approximated by another straight line. So what one does is that this part of the characteristic you approximate by a straight line like this, and the rest of it by another straight line like this, whose slopes are different. Alright. As you will see later, such approximations are, obvious name is given, piecewise linear approximation. That is, you choose pieces of the characteristic curve, pieces of the curve. This could be a voltage current relationship, or a flux current relationship, or a charge voltage relationship. You choose parts of the curve and approximate this by a straight line. You choose another part approximated by another straight line. So these are piecewise linear approximations. For example, if the device is operating, let's say if the device is operating in this region, then obviously you can treat this device as a linear device, correct? Or the device is operating in this region, it doesn't go to low values at all, then obviously you can again approximate it by a linear device. And this is what we shall do. A transistor, for example, is a highly nonlinear device, but we shall operate it in such a region that it can be approximated by a linear device. And if we can do that, then our analysis becomes extremely simple. And a transistor used as an amplifier is an example of a nonlinear device being operated in the linear region, as we shall see in more details later. Now, besides graphical characterization, we can also have analytical characterization. What we do is, suppose we have a nonlinear resistor where I, the general characteristic of a nonlinear resistor shall be not I equal to V by R, but I equal to some function of V, alright, some function of V. And you know that such a function can always be expanded into a power series. That is, I can write this as A0 plus A1V plus A2V squared and so on. Alright. If you stop at the second term, then obviously there is a linear approximation. Alright. If you stop at the third term, then it is a quadratic approximation. If you stop at the fourth term, cubic, and so on and so forth. So more terms you accommodate, the better is the approximation. Alright. For example, if you consider a diode, once again, a characteristic of a diode, and you want to approximate it by, let's say, up to the quadratic term, that is squared term, alright. Then you notice that because I equals to 0, when V equals 0. This is I and this is V. Therefore, A0 term shall be equal to 0. That is, what I have is I equal to A1V plus A2V squared. Alright. A0 term is equal to 0 because V equal to 0 means I equal to 0. Alright. Suppose to the diode, to this diode, which is approximated by a quadratic characteristic like this, suppose you apply a sinusoidal voltage, that is, to the diode, which is approximated by I equal to A1V plus A2V squared, you apply a voltage source which is Vm sine of omega t, Vm sine omega t, alright. What would be the current? Obviously, all that you have to do is to substitute Vm sine omega t for V and find out I, and therefore the current in this circuit shall be A1 Vm sine omega t plus A2 Vm squared sine squared omega t. Alright, this would be the current. Now to see what effect this nonlinearity has on the output frequency. So the input frequency is omega, radians per second. What are the output frequencies? You notice that cosine of 2 omega t is equal to cosine squared omega t minus sine squared omega t, which is 1 minus 2 sine squared omega t, and therefore sine squared omega t is equal to 1 minus cosine 2 omega t divided by 2. Is that okay? Therefore, my current I can be written as A1 Vm sine omega t plus A2 Vm squared by 2. This is to be multiplied by A2 Vm squared. So, A2 Vm squared by 2 minus A2 Vm squared by 2 cosine of 2 omega t. And you notice that if this diode was a linear resistor, then a voltage Vm sine omega t should have a current which is A1 Vm sine, that is only this term should have been present. Isn't that right? If it is a linear resistor. What has nonlinearity done to it? Nonlinearity has brought in a constant term, a DC term, which would not have been present if the diode was a linear resistor. So nonlinearity brings in rectification. What does this mean? This is the average value. If you average out over a large interval of time, then this will be the DC value. If you put a DC meter in the circuit, the meter will read A2 Vm squared by 2. Alright, this was not there in the input. The input was a pure AC and you get a DC out of it. So there is rectification. Number 2. In addition, there is a term whose frequency is twice omega. Now, if omega is called fundamental, then twice omega is the second harmonic. Twice omega, any frequency which is related to another frequency by an integer is called a harmonic. The first harmonic is the fundamental. The second harmonic has a frequency twice omega. And therefore, this generates a second harmonic. The diode generates a second harmonic. Now, let's look at this a little more carefully. A diode with a quadratic characteristic can generate A1 Vm sine omega t plus A2 Vm squared by 2 minus A2 Vm squared by 2 cosine of 2 omega t. Suppose I arrange things such that A2 is much greater than A1. A2 is much greater than A1, alright. Then obviously the first term would be negligible compared to the second and third terms, alright. Agreed? And if somehow I can get rid of the DC term, how? If I put a capacitor in this circuit, it will not allow a DC to pass. So the current would be simply, this is negligible, this is blocked by a capacitor, so the current would be simply of frequency twice omega. In other words, the diode then acts as a harmonic generator. If your original signal, if your original input was 50 hertz, then you can generate 100 hertz from it. Alright. Similarly, if the diode had a cubic turn, you could generate a third harmonic, because sine cubed omega can be written in terms of sine of 3 omega. Alright. So, a nonlinear resistor is not necessarily an undesirable element. It can be used to generate harmonics, that is multiples of the given frequency. Next, suppose I retain only the DC term. How do I do that? Suppose I shunt the diode by a capacitor. The capacitor does not pass DC. I shunt the diode, that is I connect a capacitor across the diode. Then all the AC current, the A1 Vm sin omega t and A2 Vm squared by 2 cosine 2 omega t, they pass through the capacitor. So I am left with only the DC component, and therefore the diode can be used as a rectifier. Alright. Suppose yet another instance. Suppose I get rid of the DC term by using a capacitor. I get rid of cosine 2 omega t term. I reject it by means of a suitable circuit. Then I shall be left with A1 Vm sin omega t. And if A1 is greater than 1, don't you see that this acts as an amplifier? If A1 is greater than 1, then the maximum amplitude was Vm, now I have increased it to A1 Vm. So a nonlinear resistor is not necessarily an undesirable phenomenon. It can be used to your advantage in a circuit. Yes.
So in this case, when you are talking about amplification, so we are getting a A1 Vm term if A1 is greater than 1, but this is the current in the circuit and not the voltage. Whereas what we have applied is the voltage.
That's right. So you drop it across the resistance. You pass this current through a resistor and get the voltage. The voltage can be greater than the input voltage. You are quite right. A1 Vm sin omega t is not a voltage, it is a current. So what all you have to do is pass it through a 1 ohm resistor, then this current will be converted to a voltage. Alright? Good. Now let us take an example. This example concerns, I want you to follow this carefully. This is the first acquaintance with the style of analysis that we shall adopt in electronic circuits. We have a linear network N which is feeding a nonlinear resistor Rn. The nonlinear resistor Rn is characterized by a voltage current relationship which is, let us say, V equal to f of I, some function of I. As I had said earlier, f of I could be approximated by a power series which has to be truncated at a certain power. Alright. What we are interested in is to find out the value of V and I when the linear network N is excited, that is, it contains resistors, voltage sources and current sources. There can be dependent as well as independent voltage and current sources. We are interested in solving for the voltage and the current across the nonlinear resistor. This is a special kind of a circuit. The linear network is being considered as a driver and the nonlinear resistor is being considered as the driven element. Alright. Now, since this network is linear, we can always replace it by its Thevenin equivalent. So, let us say we have a Vt, then in series with Rt, alright. This is the equivalent of the linear resistor. Then we have the load, which is Rn, and the voltage and current are V and I, alright. How do I find out V and I? That is the question. If you look at this circuit, once again, the Thevenin equivalent Vt plus minus series Rt, then Rn, V and I, you see that one of the relations that V and I have to satisfy is that V equal to function of I. This is because of the constraint by the nonlinear resistor. This is the nonlinear resistor characteristic. You also notice that V must be equal to Vt minus IRT. Therefore, V and I must satisfy this as well as this, which means that you have to solve these two equations simultaneously to get the values of V and I. In a linear resistor, finding out either the current or the voltage suffices. In a nonlinear resistor, no. You have to find both. You have to find both V and I, because V and I are not related by a simple relationship. Alright. So how do you solve this? You solve it graphically. Okay. You solve it graphically. That is, what you do is you make a plot of V and I. Alright. Let us say that V equal to Fi, this nonlinear relationship is, let's say, like this. V equal to Fi. And suppose V, small v equal to Vt minus IRT. What kind of a curve does this represent? Straight line. And this straight line is something like this, where this value corresponds to what? This value corresponds to V equal to 0, and therefore Vt by RT, and this value corresponds to I equal to 0, so this is equal to Vt. So all that you have to do is to locate the point Vt on the voltage axis and locate the point Vt by RT on the current axis and join them by a straight line. Obviously, the solution to this circuit is the intersection between the two graphs, because V and I have to satisfy both of these equations. And this is the style of solution that we adopt for all transistor or active electronic circuits that we shall study later. This red line is called the load line for reasons to be understood later. This red line is called a load line, and this is the device characteristic, and it is the intersection between the two which determine the current and voltage. As I said, both are required. It is not sufficient to find out the voltage only or the current only. Both of them have to be specified. And it is in this context that we shall take a fairly non-trivial example. This example concerns the series connection of two nonlinear resistors, a 30 volt source in series with 5K. This is connected in series with two nonlinear resistors A and B. Alright. Two nonlinear resistors are connected in series, and the characteristics of both A and B are given. What do you mean by characteristics? A plot of I versus V or V versus I. This is given. What you have to do is, if this voltage is V, the composite device, that is A and B in series, and this current is I, the first thing you have to do is to have the composite characteristics, that is plot I versus V. How do you do that? Add the two graphs. That is, you know I versus VA and you know I versus VB. So set a particular I, read VA and VB, add the two, and plot a new point. Let me show you. I have actually done this. Is this graph visible? Yes? Okay. So this is the characteristic of the device A, this is the characteristic of the device B. So what we do is, for example, take a current of 2 milliampere. I read V1, VA, let's say this is about 2, alright. I also read VB, that is the other curve, and this is about 11. So 11 plus 2 is 13, and this is what I plot here, 13. This orange curve gives the characteristic of the composite device. That is, I fix 1 milliampere, 2 milliampere, 3 and so on. At each value of current I read VA and I read VB, then I add VA and VB. So this is the characteristic. Alright? Okay, you don't have to draw this. It is it's a problem given in the textbook. You could take that and work it out yourself. Now the next question is, you have plotted I versus V. Let's say this is the characteristic. Then what you are required to find out is I and V for this circuit, for this particular circuit. I versus V is one characteristic. The other, the load line, obviously is given by V equal to 30 volt minus 5000 I. Is that okay? V, this voltage is equal to the source voltage 30 minus the drop in 5K, that is 5000 times I. And you have to plot this line also. This is what I have plotted here. This blue line is the load line. For example, when small v equals to 0, the current shall be 30 divided by 5000, which is equal to 6 milliampere. That's the point. When small v is equal to 20, then 30 minus 20 is 10. No, this is not clear what I am doing. Okay, look at the load line. When small v equal to 0, I equal to 30 divided by 5000, which is equal to 6 milliamps. When small v equal to 20, then I equal to 30 minus 20, that is 10 divided by 5000 amperes, which is equal to 2 milliamps. 2 points are enough for a straight line. So I mark this point and join them by a straight line. So the intersection gives me the values of V and I. And you can read this as small v, I read that as 15.5. This is 15.5. And small I, that is the current, is about 2.9 milliampere. So I know the current and I know the composite voltage. Do I know the individual voltages? No? Well, 2.9, wherever it intersects the curve A is VA. Wherever the line intersects B, I know VB. So I know VA and VB. Then do I know the power dissipated in the two resistors? Yes, I do. The current is the same. You multiply the current by the voltage. And the end result, my end result is that VA is equal to 3 volt. You can verify this. This is a problem given in the textbook. VB equal to 12.5 volt. So PA and the current I is 2.9 milliamps. So PA is 8.7 milliwatt, 3 multiplied by 2.9, and PB, the current, the power dissipated in the resistor B, is 2.9 multiplied by 12.5, which is 36.25 milliwatt. These are my results. And this is a fairly complicated example, all right. As an exercise for you, to bother about. Let's say A and B are connected in parallel. Then how would you solve the network? If A and B, instead of series connection, add the currents, and therefore you have to take this characteristic in the other way, that is, the voltage is the same. So for example, if the voltage is 10, then you have to read the current from here and you have to read the current from here, then add the two currents. Well, I leave that to you as an exercise, but should we drive them by means of a voltage source or a current source? Can we work out the same circuit, that is a 30 volt source, 5K, then A and B are in parallel. What I want to find is VI, also IA and IB. Can I do that? Yes, why not? Or is there a specific problem? All that you have to do now is to fix the voltage. To draw the characteristic, take a certain voltage, draw a vertical line and see what the values of the currents are in the element A and in the element B. Add the two currents, that you get I, and therefore you can plot V versus I. Then on this plot you draw the load line, mark the intersection, that gives you V and I. Then you divide between IA and IB. Alright. This, yes.
But the load line for this, that will be, so I is equal to.
Load line will be the same. That is V equal to Vt minus 5000 I, where I is in amperes. Load line will be the same, because this V is this voltage minus the drop in 5K. Alright, is that okay? Now one tricky question is about the superposition theorem. The superposition theorem, I told you that the current or voltage in any element can be obtained as the superposition of the current and voltage that would have existed if each source acted independently after killing all other sources. Alright. Now, can I apply this principle to the calculation of power? That is, I have an element, let's say R, and I wish to find out the power consumption, power consumed by R. I find the power due to one source acting independently. Why not? Because I squared is not equal to I1 squared plus I2 squared and so on. Alright, that's the reason. Superposition does not apply to relationships which are not linear. Alright, voltage is IR or current is V by R, and therefore you can add V1 and V2 and obtain the. Now this mistake is very often committed by students. Power cannot be obtained, power, energy, they cannot be obtained by superposition. It is only voltage or current. Next time we go to a new topic, that is different types of signals and their processing. That's all for today.